Welcome back to the Explainer. Now, our last explainer talked about how this playlist is going to be your step-by-step guide to understanding tensors and how they power modern artificial intelligence and machine learning systems. We started from the absolute basics, but today we're gradually moving into how those tensors are actually used inside neural networks, deep learning models, and frameworks like PyTorch and TensorFlow. Specifically, we're moving beyond just text to uncover how modern AI actually processes the visual and auditory world. If you've ever wondered how models can literally look at a picture and tell you exactly what's inside it, you are absolutely in the right place. So let's just dive right into this truly fascinating question. How do you teach an AI to see? Because teaching a language model to actually understand an image, it fundamentally changes everything about artificial intelligence. It bridges that massive gap between just processing abstract words and truly understanding our physical reality.
We've got a packed roadmap for you today. We're going to hit the multimodal revolution, look at the anatomy of these models, break down their 3 stages of training, explore exactly how AI sees images, and finally, do a real driving test with Google's Polygamma.
All right, let's kick things off with Section 1, the multimodal revolution. Over the past year, it's been wild to watch. Models like GPT-4 Vision and Gemini didn't just get better at writing. They started handling images, audio, and even video. We're essentially giving these AI brains sensory organs. They're no longer confined to just text, They process multiple data inputs to understand the full spectrum of the world around us. So how is this actually built? Let's move to Section 2 and look at the anatomy of these multimodal models. It helps to think of this like biological anatomy. The whole system relies on 3 core components. First up, the pre-trained LLM acts as the brain, handling all the text generation and logic. Second, you've got the modality encoders, acting as the eyes or ears. These are pre-trained models like convolutional neural networks or vision transformers that process the raw input. And finally, we need a way to connect the two, which brings us to the modality interface. This interface is absolutely crucial. It's typically a multi-layer perceptron acting just like an optic nerve. It takes those raw visual signals coming from the eyes and translates them directly into the mathematical tensor embedding space that the brain already understands. It's the ultimate translator. Next up, Section 3. Now that we have the body, how do we educate the model? Well, just like training a text-only model, we follow a pretty rigorous 3-stage curriculum. Step 1 is pre-training, where we align the different modalities using vast amounts of web-scraped data, essentially teaching the model to predict captions for images. Step 2 is instruction tuning, which is teaching the model to follow very specific tasks like object detection. And Step 3 is alignment, matching those outputs to what humans actually prefer to ensure the AI is helpful and safe. Now, there is a really clever strategy at play here during that first step. By freezing the parameters of the brain and the eyes during pre-training, we avoid inadvertently losing that pre-trained knowledge. If we mess with them, the AI would basically suffer from amnesia and forget all the fundamental rules it already learned. So we literally only train that connecting optic nerve interface at first. Okay, moving on to Section 4. Let's zoom in on exactly how the AI sees these images. Instead of reading left to right like a book, a vision transformer, or VIT, chops an image into fixed-size puzzle pieces. It treats these pieces exactly like words in a sentence, using that famous self-attention mechanism to capture how every single piece of the image relates to every other piece. The magic number here is 16 by 16. The image gets divided into these 16 by 16 pixel patches. Those patches are then flattened out into vectors, which, as we know, are just tensors under the hood. They're embedded with linear projections and combined with positional embeddings, so the AI always remembers exactly where each puzzle piece belongs in physical space. This brings us to a massive paradigm shift in how we teach these models. Traditionally, convolutional neural networks forced an AI to rigidly label an image from a fixed list, like this is a cat or this is a car, completely discarding all the finer details. But contrastive learning works totally differently. It trains across massive datasets of image caption pairs, teaching the model to semantically align text and images like a gigantic, super nuanced matching game. In this contrastive approach is a total game changer because it gives the models incredible zero-shot capabilities without needing specialized training. For example, OpenAI's CLIP is highly effective, but it's pretty memory intensive because its softmax loss mechanism requires calculating a massive pairwise matrix. Compare that to Google's SIGLIP, which uses a sigmoid loss mechanism to evaluate individual image-text pairs. That makes it incredibly scalable and way more memory efficient. Let's put all this theory to the test in Section 5. It's time for some hands-on with polygamma. Google's open-weight polygamma beautifully maps to that anatomical diagram we talked about earlier. Under the hood of this 3 billion parameter engine, it combines a SIG-LIP vision tower with 27 encoder blocks acting as the eyes, and a Gemma GPT model with 18 text decoding blocks acting as the brain. Connecting them is a simple multi-layer multi-model projector. But how do we actually ask it a question? Well, the preprocessor formats our inputs by taking a text query, say, describe this image, and appending a series of identical image placeholder tokens. Before the model actually processes anything, those placeholder tokens are mathematically swapped out with the actual visual patch embeddings we discussed a minute ago. And when we test it, the results are honestly stunning. Fed an image of a peacock standing near a house, the visual Q&A flawlessly identifies the pink flowers in the scene. It just answers, they're pink. This proves that the text and vision alignments are working perfectly in tandem. But it doesn't stop there. Polygamma features semantic OCR. It can read a blurry, shadowy receipt to calculate a $100 total, or pick out the author Caro from a picture of a book cover. The absolute key word here is semantic. This isn't just basic text recognition. The AI actually understands what it's reading. It knows precisely which part of the book cover represents the author versus the title. And this perfectly demonstrates its object detection skills too. When you give it the prompt detect flowers, the AI doesn't just describe them, it returns 4 precise coordinates forming an accurate bounding box. It can physically locate specific requested elements, like the flowers or the house, right there in the image. We've seen how vision transformers and modality interfaces give LLMs true eyes and ears, transforming vectors and tensors into an incredible understanding of our physical world. It kind of leaves you wondering, right? Just how far is this multimodal evolution going to go? As AI completely masters sight and sound, what human sense will it conquer next?